Hello again. Today we're going to start a new unit called momentum. Momentum is the basic idea behind the phrase, an object in motion stays in motion. Let's take a closer look. Momentum can be described in a number of ways, but the simplest is probably just to call it the quantity of motion. It's really a combination of two different things as specified in the definition. The definition of momentum is mass times velocity. Now before we begin, this P is the symbol for momentum. We had to use a different symbol because M was already taken for mass. So you recognize M here as mass, that's things measured in kilograms, and velocity, that's things usually measured in meters per second. Notice the arrows above the P and above the V. That indicates that momentum and velocity are both vectors, which means the direction is important. Now the units of momentum would be relatively predictable. Since it's a mass times a velocity, it should be a mass unit times a velocity unit. The standard units for momentum are kilograms for mass times meters per second. That's the standard unit for momentum. There are other non-standard units that are possible too, and that's just any other type of mass unit, say grams or perhaps pounds, and any other type of velocity unit, for instance miles per hour or feet per second or knots. So a particular momentum unit could be a pound knot if you want, although we're pretty much going to stick to kilogram meters per second. So, quick example. Which has more momentum? This 4,000 kilogram fire truck moving at a measly 20 miles per hour, or a 1 kilogram baseball that's thrown at 95 miles per hour? Calculating momentum is simple enough. Momentum is the mass times the velocity. So, in the case of the fire truck, it's 4,000 kilograms times 20 miles per hour, or 80,000 kilogram miles per hour, which is not the standard unit, but if we calculate the baseball's momentum in kilogram miles per hour too, we can compare the two. We'll do that quickly enough. The momentum of the baseball is the mass of the baseball, which is just 1 kilogram, times the velocity of the baseball of 95 miles per hour, which corresponds to just 95 kilogram miles per hour. Now that should make sense to you. You see catchers at the baseball game standing in front and stopping the ball, but you seldom see that same catcher go out after the game and stand in front of a fire truck, even if it is only moving at 20 miles per hour. The fire truck is a whole lot harder to stop. Another example is, what's the momentum of the Earth as it's traveling around the sun? I imagine this number is going to be huge. First of all, the mass of the Earth is huge, and it's traveling pretty quickly around the sun. For all practical purposes, we're never going to have momentum this high in our problems, but I just wanted to illustrate a little bit to you the immensity of the planet that we live on. To begin, we'll calculate momentum is the mass, but we need the mass of the Earth, times its velocity as it travels around the sun. The mass of the Earth is a huge number. You can look it up in the back of your textbook if you'd like. There it's listed as 5.97 times 10 to the 24th kilograms. That number's so huge, I don't even know how to say it except for by using scientific notation. To calculate the velocity of the Earth, let's draw a picture of its orbit around the sun. Here will be our sun, and out here the Earth. And the Earth travels in a circle around the sun with some sort of radius. And we know the time it takes to complete this whole circle. The time it takes is 1 year. We also know the radius between the Earth and the Sun. That same number can be looked up in the back of the book. That's 149.6. You think miles? You think light years? No, that's 149.6 times 10 to the 6th kilometers, or 149 million kilometers. The velocity that we need then is the total distance all the way around, which is the circumference. We'll have to calculate that, divided by the total time, which is 1 year. The circumference is 2 pi times the radius. That's in kilometers. And the time is in years. 1 year. And at this point, if we multiply the mass times the velocity, we'll get our momentum. Our units are a little strange. Our units are in kilometers per year instead of kilogram meters per second. But that's all right. Momentums can be in lots of different units. And unless we're going to compare this number to some other number, we can leave it in this mess of non-standard units and be all right. Our calculation then is 5.97 times 10 raised to the 24th power times 2 times pi, which is second caret, times 149.6 times 10 raised to the 6th power. And that number is so big, I again don't know how to express it without using scientific notation. Let's say 5.6 times 10 to the 33rd.